Hi everybody, welcome back. We're continuing our series on nonlinearities in linear regression. And so in the last video we looked at how we can incorporate quadratic formulas and relationships into a linear regression model whenever we have some the quadratics occur if we're trying to model something that has a diminishing sort of effect. And the example we used was experience on wages. So in our early years of our career, experience or wages increase quickly as we add more experience. As people toward the end of their career, that wage will start to flatten out. And so that's accomplished by including a squared term in the regression equation. So it's still a linear regression because it's linear in parameters, but we have a nonlinear functional form for our x variable experience. We're going to continue with nonlinear functional forms, but in this video we're going to discuss log models. So we're going to discuss two of them, LogLevel and LogLog, and I'll explain what those are, what those mean as we go. We're going to start with LogLevel. All right, and again, we'll do this by way of example. Ultimately, the reason why we might use a LogLevel model is similar to the reason we may use a quadratic model. Ultimately, we're trying to think very carefully about how the relationship we're modeling works in the real world. And so now, instead of looking at wages based on experience, let's look at wages based on education. So wage is equal to beta 0 plus beta 1 times years of education plus our error term. That's the model we're estimating. The estimated version of the model is our predicted wage and our estimated regression coefficients beta 0 and beta 1, education. So we will run this model in Python, and when we do, we're going to, in a separate video, we're going to find the following results. Beta 1 is going to be negative 0.90, and beta 1 is positive 0.54 times the years of education. So, as we would expect, there's a positive relationship between education and wage. Hopefully we know how to do this, but let's go ahead and look at the interpretation of beta 1. This is saying that each additional year of education is associated with a 0.54 or a 54-cent increase in the hourly wage. And then again, ceteris paribus, all else held constant. Okay, so this on the surface sort of sounds okay, but if you start to think about what this means, this education variable is linear, so it's just a normal linear variable there. And what that's saying is that if you go from first grade to second grade, you've added a year of education, so you're going to add 54 cents to your hourly wage. But that's the same thing as saying, but this model assumes the same thing if you're going from your second year of law school to your third year. It's a plus one. Both of these are plus 1 year of education. So you go from your second to third year, your last year of law school, you're going to add 54 cents to your hourly wage. And so this is where the problem may be. And ultimately, we would think that as you add more years of education, you should be having increasing returns to scale. But we would think more years of education have increasing returns. And so a better characterization of how wages change is by how wages change with each marginal year of education is by a constant percentage. And that's going to give us the same thing. That's going to give us a constant percentage is going to give us increasing returns. And so instead of thinking as going from the first grade to the second grade as plus 54 cents, we might think of it as increasing by 8%. And we could also then think of going from the first year of law school, second year to the third year of law school, also as 8%. But if you're moving all through grade school, getting 8% every year, when you're adding percentages every year, you're getting that compounding. And so it kind of works in a way like compound interest. And so in the end, if you keep adding by a constant percentage, you're going to get increasing returns to scale. So instead of 54 cents every year, you're going to get an increasing returns to scale as you have higher and higher levels of education. And now I want to just briefly show you a little bit of an example of that if we do a very basic simulation inside of Excel. Okay, so here's a little Excel file where I've kind of simulated the idea. You've got years in school, 1 up through 12 for grade school, college 4 years, and law school 3 years. And we could have a simple linear regression where we just add, and so these are just hypotheticals. We're starting at $100 in both. If you add $8, you go from 100 to 108. You add 8%, you go from 100 to 108. But with the linear model, you're just adding 8 every single time. You've got that linear relationship there. But if you're adding a constant percentage, now you're adding 8% to 108, and it's going to add that little bit extra. And you're starting to compound, and you're going to start to see exponential growth. And it's exhibiting this idea of increasing returns to, in this case, an education. But in general, if whatever you're modeling might exhibit this increasing returns type behavior, then you might consider using a logged variable for your x variable. Just like in the last video we saw, if you have decreasing marginal changes, you would use a quadratic squared term. Okay, so in any case, this is what we're after here. And in doing so, we're going to get a more appropriate model. So this is called, so by a better characterization is through constant percentages and a log level model will approximately give, a log level model gives us this being constant percentages. And so this is also going to give us the constant percentages and the increasing returns. And when we're saying log level, what we're meaning is the log is the y level, the y variable will be logged with the natural logarithm, natural log function, and the level is just measured in normal either dollars or whatever normal units, but not logged units. So essentially what we have is, let's take the same original equation where we have wage is a function of education. But the log level model is the log of wage and then the right hand side is the same. So we have log on the y side, level on the other side. In the next video we'll talk about log, and then we would just do log of education and log of wage. That would be log. This is log level because this is measured as normal. Okay, and so now the way so one, this is good to give us a relationship that we want here. The log model will give us that increasing returns. And then we can start thinking about interpretation. So the percent change in wage is going to be approximately equal to 100 times beta 1 times the change in education. So let's write that slightly differently. Basically, if we take this equation here and we take the exponential of both sides, so we have the exponential of the log of the wage is equal to the exponential of beta 0 plus beta 1 education. Well, e to the log of x is just equal to x. These are reciprocals of each other. And so that goes away, and that says wage is equal to the exponential of beta 1 times education. And that is why we're saying that wage is an exponential function associated with education. And that's why we get this exponential graph here. Y is equal to e to the x is essentially what that is. Except here, x is education, y is wage. Okay, and so we can estimate that, and we get some output that might look like this. So if our log of wage estimation comes out as follows, which again we'll do in Python in a follow-up video, 0.083 times years of education. Let's look at how we interpret that. So each additional year of education is associated with a 0.083, or, and this is the nice part, 8.3% increase in the wage. Increase in wage. Ceteris paribus, all else equal. So the log level interpretation allows us to interpret the beta 1 coefficient as a percentage increase, which is, maybe I should put this down here. It allows us to interpret the beta 1 as a percentage increase of x associated with y. So it's a really nice way to interpret variables. So that's kind of the specific one. The more general one is, because logs are approximate, there are some special rules. That's equal to 100 beta 1 times change in x. Okay, yeah. And so, again, the main reason to do a log level model is to get this relationship with an exponential relationship. That'll do log of y, a function of x. In the last video, we saw if we want a diminishing relationship, we do y is a function of x and x squared. So we have the x squared term in there. And then finally, in the last video for this series, we're going to do one final model, which is going to be called log model. And so these are the possible relationships here. The nice thing about the log model is that this is going to help if we want to get some elasticity estimates. So this is a constant elasticity model. Okay, and so anyway, that's going to be what we look at for the next video. Yeah, and like I said, for all of these, we're going to do some examples in Python. But yeah, we're gonna move on for the last video to log. So I'm going to stop this video here and pick it up in the next one. Hope to see you there. Thanks.